Hi, I'm Antonio Sala, and in this video we are going to continue with an example of multi-output Gaussian stochastic processes, and in particular we will discuss prediction given some samples of such processes. If we summarize what we did in previous videos, we may consider two variables that depend on an abscissa, let's say temperature and humidity given latitude, and we may assert or identify from data statistical model saying that the increments with respect to the mean have some correlation, so above average temperature observation may correspond to above average, let's say, humidity observations. The idea of multi-output stochastic processes was discussing how, using that correlation, I may use temperature samples to improve my predictions about humidity or vice versa. That was the idea, and the statistical model could come from stochastic differential equations and things like that, with deep theoretical interest in signal processing, filtering, whatever, but we are not considering that, and we are just considering that we draft a hypothesis that my observables y, functions of x, are a combination of, let's say, three independent components, independent stochastic processes that are, superimposed with a given C matrix. In this case, we will have a -1 there. So under that assumption, y equals Cu, the covariance of the outputs will be a 2 times 2 symmetric positive definite matrix given by C and the covariance of my components, which will be a diagonal covariance kernel times C transposed. But we also discussed in previous videos that instead of considering a 2-output stochastic process, which are 2 by 2 covariance, we can just consider things to be a 1-output stochastic processes with an extra input, which will be an index, so that 1 will refer to variable 1, 2 will refer to variable 2, and if I call this augmented input as U, then I will need to define a covariance kernel between U1 and U2, being each of those U augmented inputs comprised of an abscissa coordinate and an index. So this should return the suitable element of this covariance matrix, 1, 1, 1, 2, 2, 2, whatever. And we could extract that element in this C transposed using just the I1 row of C at the left and the I2 row of C at the right. The thing is that we ended up programming an example with these three independent factor covariance kernels, let's say, this C matrix in which, the common factor goes, in this case, in opposite phase, changing sign, let's say, in one output and in the other output. And we were able to program this C, the diagonal component covariance C transposed, or, the thing we are going to actually use with an augmented input, as we discussed a minute ago, being an equivalent representation. So we will use this, and then we are going to make prediction, but let us just remember the kind of process we were dealing with, which had this sample realization, let's say, to random functions that, somehow were correlated in the sense that there was a common factor, like here, the yellow dashed line that had opposite sign in each of the observables y1, y2, and then some higher frequency wiggling due to the non-shared components. So how can we do predictions in here? Well, it's easy in the sense that once we have the augmented input representation, this is just an augmented input that could be, named C or whatever. The thing is that once we have this augmented input, then our best prediction formulae are exactly the same as in single output Gaussian processes. So nothing else to be said from a theoretical point of view. So the only thing is that we are going to discuss a little bit of details of code and plots and intuition in the interpretations, but from an abstract point of view, 2-output Gaussian processes are nothing but one output Gaussian processes with a higher dimension input. So theory is finished, but okay, let's discuss prediction. Then, as usual, if I have augmented input consisting of an abscissa and an index, 1, the blue thing, 2, the red thing, label, we could say, instead of index. Well, the thing is that if I have some measurements at a given abscissa, at a given label, I can get the covariance of this information. We'll assume 0 mean to avoid cluttering. Otherwise, this will be the increments over the mean. Well, the thing is that I can get this covariance of the information, and the best prediction will be the covariance between the test points I wish to predict and the information times the inverse covariance of the information, and the posterior residual variance will be the prior covariance between test and test points minus covariance test info times inverse of information covariance times same stuff but transposed. So these are the usual best prediction formulae from, say, Wikipedia. We are saying just this Wikipedia thing with a different notation. So, well, nothing new theoretically, so let's go with our examples. We will assume that we have these blue samples from first function, temperature, let's say, and red samples from our second function. And I know that there is a common component in opposite sign, let's say, and so, well, we need to interpolate and extrapolate using these two samples. I will encode that with these data x and index. First column will be the abscissa, second column the index, 1 blue sample, 2 red sample, and the abscissa, and data y will be the actual value. So we'll some straightforward plotting. I get these things, and then we wish to do Gaussian process regression to predict what happens in the middle in mean and confidence interval. I will put some measurement noise variance identical for red and blue samples, and we'll discuss the code in a minute. We get this plot, which is the main goal of this video, to jointly improve the red prediction via the blue samples and vice versa. So we get this blue and cyan mean and confidence interval, 2 standard deviations for the function f1, the first output, and the red and pink mean and confidence intervals respectively for the second function. And you see that there is some kind of opposite sign, let's say, of the predictions as postulated by my model. So how do we carry out these computations? Well, computing these covariances, that of course, once I have this function in my MATLAB workspace, it is just standard Gaussian process regression. With this, I compute the prior variance between my test points label 1, test points label 1. With this, I compute the prior variance between my test points and label 2, test points label 2. With this, I compute the covariance matrix of the information points. Column 1 is the abscissa, column 2 is the label. And with test 1 info, I compute the covariance between test points label 1 and the information, ending here test points label 2 and my information, so I have the suitable covariance matrices to program these expressions here. In mean, the covariance between the test points label 1 and the information times the inverse of the information variance times the data. This for the f2 function. This is the posterior variance formula for points with label 1, and this is for points with label 2. Standard deviations for plots are the square root of the diagonal, and that's it. I mean, you can just pause. Well, I didn't say that the information I added identity times noise variance. But okay, if we had different measurement noise for the blue samples versus the red samples, then I would need to add a diagonal matrix with a suitable variance for each measurement and not just an identity times a constant. But okay, that's just implementation detail. So I just put the same variance for all sensors. So well, if you pause and examine this code, you will realize that there is nothing different to the well-known Gaussian process regression formula. So after some plotting commands, we get this prediction in mean and confidence interval we were discussing. And this is our main goal. But okay, a question arises. I mean, what would have happened if I had just used standard Gaussian process regression just with the blue samples to predict blue and the red samples to predict red? That would be, let's say, the marginal predictions, and not exploiting the correlations between the blue and red functions. Well, we can do it with, again, standard Gaussian process regression. You can just download the code and inspect it. And if we see, for example, the difference between this joint prediction of the blue F1 thing and the marginal one using only the blue samples, then we get, after this other covariance with IDX1, only the samples with label 1, etc. Download the code and inspect it at your own pace. Well, the thing is that this is the posterior plot in green with only the marginal blue points, and in blue and cyan the joint prediction. And well, we see that predictions are different and that the joint prediction in blue cyan has narrower confidence intervals. Indeed, I mean, it seems to be so, but if we just plot the standard deviation, forgetting about the mean going up and down, then in this plot we see that when we have samples of the blue F1 function, then we get basically a perfect knowledge of what the function is there, because we have a very small measurement noise variance. The vertical red lines indicate points where samples of the function 2 are available, and then the green curve is the standard deviation of the marginal using only samples of 1, and when I have samples of function 2 in the middle of samples of 1, then the cyan plot here has a reduced standard deviation of the residual error. So information about the red samples contributes to improve my predictions about the blue ones, as intuitively expected due to the correlation between them. And if we do the same with the second function, these are the posteriors in red and pink using samples of both red and blue functions. The vertical lines indicate the points where samples of function 1 are available. And then if we did not use those samples of function 1, that of course cannot be presented here in this plot because we are plotting function 2, not 1. But if we use these samples in the statistical posterior computation, then the magenta confidence intervals are narrower than the yellow ones, which are from the marginal prediction using only the red samples. Indeed, if we plot the standard deviation, we get that the red curve is the marginal standard deviation, that okay, it's very small at points in which I have a sample of the red function, but if I use the blue samples to predict function 2 red, then I get smaller confidence interval of that improved prediction. So this is the basic idea, and indeed we are going to bring it to the limit by discussing a second example in which we will have only observed points of the blue function labeled 1, these theta y points, but they will be helpful to predict function 2 because, okay, a very important common component is just function 1 negated. These are the samples, all of them above 0. And then, if we apply the same code, we get that the best prediction of F2 is sort of the blue line smoothed and changed sign, which is the red mean here, and we have the pink confidence interval that is somehow narrow when I have samples of function 1. It does not shrink to 0 because I do not have actual samples of function 2, but okay, at least it helps something. When I have no samples of anything, then both function 1 and 2 confidence intervals widen to the prior, let's say, no information case. So if I now plot this confidence interval compared to the prior in the red pink we are estimating, if I had no samples of F2, my marginal prediction would be just the prior 0 mean plus minus 2 standard deviations, 6 point something, but my posterior with the information from blue function is the red pink stuff. And if I compare the width of the residual posterior variance, here I have it. I have like 3.1 or something like that marginal uncertainty of function 2, but thanks to the samples of function 1, then I can reduce my uncertainty to the blue thing, the posterior of function 2, only knowing the samples of function 1. So with this second example, we finish here. Let us summarize. In this video, we have discussed how to make predictions, extrapolation, Gaussian process regression from samples of a multi-output Gaussian process in which I had, a common component with opposite sign and some higher frequency wiggling in each of two functions. I had samples of both functions, and by suitably using them in a joint way, I was able to improve over what we would say the marginal Gaussian process regression, in which only sample of my same color might be thought to be used for prediction. Then, of course, the joint analysis, given that we exploit the correlation between the functions, helps us improving our predictions. So we get this kind of mean and confidence interval results, whose confidence intervals are, of course, narrower than the standard Gaussian process regression that I could have thought at first glance to carry out separately for each of the two functions. With this, we finish the video here. Thanks for watching.